First off, thank you. Let's thank Instacart for providing all the food, the pizza, and this beautiful venue. And so we have two speakers tonight. First is Jagannath, and the second speaker will be Jeremy. I'll just keep the introductions really short so that we can get to the talks. So without further ado, let's give a round of applause to our speakers.
Hello, everyone. Thank you for coming today. I hope you all had a chance to get some pizza and drinks. If not, they're over there. Feel free to grab some. There's going to be two talks. Of course, Jeremy is going to talk about deep learning at Instacart. I'll be talking about something that's not quite deep learning or machine learning, but it's more on operations research, but I think it'll still be interesting to a lot of you. So, by the way, I'm Jagannath. I'm a data scientist here in the logistics team. I've been at Instacart for about 1 year and 10 months now. And that's me. So let's begin the talk. Let's try to understand first what we are trying to do with a couple of vanilla examples. If you take the case of McDonald's, there is a single server, for example, and this person it takes 5 minutes to serve one order. And that means we can do 12 orders per hour. And each customer is served only by one server. Now, to maintain an equilibrium between supply and demand, it's pretty easy, right? If you have 24 orders per hour, you need 2 servers per hour. If you have 60 orders, you need 5. It's pretty easy to maintain demand and supply equilibrium in the case of a single server queue. In case of Chipotle, things become a little more tricky. There's like 4 or 5 people serving you, and they all have different service times. Especially the cashier has a very different service time from the person serving your, filling up your burrito bowl, right? And now, how do we maintain supply and demand equilibrium? It gets a little more tricky, but still not crazy. We can figure something out. Of course, in the case of Chipotle, there's always 4 or 5 people. The demand is probably never that high, especially after the E. coli incident. But let's move on. What about Instacart? Turns out it's a lot harder and much more complicated, and that's what this talk is going to be about. What I'll cover in this talk is a brief introduction to some of the logistics problems at Instacart, the fulfillment models we use to do our logistics, and then I'll introduce the problem formulation for supply optimization and get into the framework we use to solve it. Because I only have 20 minutes, I'll not be covering any of the technology stack related items or algorithm technical details or get into the results and comparisons with like other on-demand models or anything like that. So let's look at the delivery logistics problem. Oh, thank you. Our customers place orders on Instacart app or on the website. We send these orders to our shoppers who see them on a separate app called the shopper app. They see a list of items that need to be shopped for. And then we deliver these to our customers. And very often we do more than one order in a trip. So the last image, we call this one batch. This batch has 4 orders, for example. Now we use 2 different types of fulfillment models to do our logistics. Let's say we have 3 orders, each placed during 3 different times, and they're all due in different windows. In one model, we use what are called in-store shoppers. These people are just within a store, and they do only picking. They don't do anything else. They pick the items, put them in grocery bags, and put them in a staging area in some shelves. And then a delivery driver would come and pick these bags and deliver them to the customer one by one. And there is a handoff process in the middle. So we call this the handoff model. By the way, this is an example of a staging area we have at a store in Austin. You can see that we have separate sections for like regular bags, freezer and frozen. It's very neatly organized. In the other model, we have what we call full service shoppers. They do everything. They do picking and delivering to the customer, and they do it all sequentially. Of course, we call this the full service model. Now, finally getting to the problem itself, on any given day, we have to do logistics, and we have a city, for example, San Francisco in this case, where we have stores with in-store shoppers. We have full service shoppers spread across the zone, and we have a bunch of orders from our customers that need to be delivered. And so we have to figure out how best we can get the orders delivered to our customers through our shoppers in the most efficient way possible. But what is efficiency for Instacart? For us, it's the number of deliveries we do divided by the time taken for doing these deliveries. If you break this down, there's two components to it. It's deliveries by active time times active time by total time. Now, active time is the time spent working on a batch or an order. It does not include any time that the shopper or driver spends waiting to get a batch. And total time is their entire shift length, the entire time they committed to work for Instacart. And the first component represents active efficiency, and the second component represents utilization. Active efficiency is about how fast we do things, and utilization is how busy we keep our shoppers. Now, to maximize our efficiency as much as possible, we need to improve both of these at the same time and get both of them as high as possible. Of course, utilization cannot be more than 100%, but active efficiency can still be as high as possible. To really improve efficiency, we need to break this down into smaller components and understand what goes on when a shopper is working for Instacart, so that we can figure out exactly how we can affect each of these different small components that happen in a shift. For example, a shopper begins his or her shift, and they do one or many of these activities again and again until their shift ends. If it's an in-store shopper, they would do just picking and waiting for a batch. They would get on their shift, wait for a batch, they would pick the items, stage them, and then go back to waiting for a batch. If it's a full-service shopper, they would start by waiting for a batch. Once they get it, they drive to the store where the batch needs to be fulfilled, and then they would pick these items, and then they would drive to the customer's address, and then they go back to waiting for a batch. And then we have delivery drivers who do all this, but without the picking part. Instead, they go pick up the bags from the store, which have been staged by our in-store shoppers, and then they deliver to the customer. And each of these activities have some times associated with them that we define. Let's try to see what they are. Like, the first one is driving time. This is the time taken for the shopper or the driver to get to the store from wherever this person is. And the factors that influence driving time are batching. Like, if we have more orders in one trip, the time spent for that trip or batch gets amortized over each of these orders. So the more we batch, the lesser time we spend per delivery, and that directly affects our efficiency. Of course, it also depends on how close the driver is to the store and traffic conditions. And the next one is picking time. This depends on how fast the shopper is. We have some shoppers who are inherently very fast. They have a pretty good mental model of the store, whereas some that are not as good, especially the new ones, take some time to get better. It also depends on the list sorting. The shopper app has a list of items that the shopper needs to pick. And depending on how efficiently we sort this, they can do things in a faster way. And this is exactly what Jeremy is going to talk about next. It also depends on the checkout times at the store. If the lines are really long, then obviously it takes more time to pick the items. Then we have the bags pickup time. This depends on how neatly organized or how accessible the staging area is. We have some stores in New York City where the staging area is in the basement because everything is so cramped in New York. So we have to find innovative ways to find staging areas. And of course, that presents a huge overhead for the drivers who go out and pick these bags. And it also depends on the number of bags being picked up. If it's a Costco order, there's often big packs of water bottles or like huge orders that take a long time to pick from the staging area and put it in your trunk and deliver. And then we have delivery time, which is the time taken to deliver an order to the customer, either from the store to the customer's address or from one customer's address to another customer's address. This depends on, of course, traffic and how densely packed our volume is. If all the addresses are next to each other, then we can form a very efficient route and the time taken per delivery goes down. It also depends on how good our routing algorithms are. If it's a very greedy approach, then we probably won't be doing a great job of minimizing delivery time. And finally, we have idle time. This is the time spent in waiting for a batch. This depends on how good the supply and demand equilibrium is. And it also depends on no-shows and cancellations. On the day of, many shoppers might choose to drop off and not work for us, and that creates a melt and lower supply than what we expect. And that affects idle time. So the first four represent how fast we do things. They affect the active efficiency directly. And the fifth one represents how busy we do things, how busy we keep our shoppers, and that affects utilization. And there's also another component to this, which is what happens when the demand is much higher than the supply. To maintain the quality of our deliveries and to make sure we deliver everything on time, we stop accepting orders after a given point. Like if the demand is far above the supply, then we have a system that shuts off our capacity and you won't be able to place an order for that day. And the next available slot will be for the next day. I'm sure many of you have experienced this if you're using Instacart. So it's important to measure and track lost deliveries cost as well when we think about figuring out how to staff our shoppers and how to do the optimization for supply. Now, I said a lot of things until now, but what am I trying to do here? Let's get to the problem statement itself. For any given day, how do we staff in-store shoppers at each store location, full service shoppers across the zone, so as to maximize our active efficiency, minimize our idleness, and minimize our lost deliveries. All these three are extremely important objectives for us, and they influence how we staff. And the final goal is to come up with something like this. At each store, at each hour of the day, we have to figure out how many shoppers we need. And also we need to figure out how many full service shoppers we need across the zone. Now, there are several factors that affect this decision. One of the most important ones is the trade-off between handoff model and full service model. Think of it as a tug of war between these two. There are some factors that benefit the handoff model. There are some that benefit the full service model. It's important to understand these. In terms of speed, as I said, the handoff model, the in-store shoppers are just in that store. They don't go out to other stores. And very often these people are the grocery store employees. They would work for the grocery store for like a few hours, stocking the shelves, and then their shift ends and they would work for Instacart, taking the items off the shelf and deliver them to the customers. So they're really good at their jobs, and their speed is much higher than the full service shoppers. So the efficiency can be really high if we go with the handoff model and do our picking with our in-store shoppers. But in terms of location, because they're so localized, they're very bad at absorbing variance, especially if the variance is high at a small geographic location, then they cannot absorb all the variance. So we definitely need full service shoppers for that. And then as I was talking about the bags pickup process, it adds a huge overhead. If you have a delivery that needs to be delivered within 1 hour or 2 hours, we cannot use the handoff model for that. So we definitely need some full service shoppers for these kind of demand that we have. And finally, task handling. With the in-store shoppers, we can parallelize the picking process. So you can imagine a situation where we pick a bunch of items or orders in advance and stage them. So we have a lot of options to create very efficient routes. And the more we do it and front load this in the beginning, in the morning, the more we can create very efficient routes. And this affects how we staff and when we staff these in-store shoppers, because we want to put more in the morning hours. Whereas this is not possible with the full service model. And everything has variance. The demand has variance, not just in terms of the number of orders we get on a day-to-day basis, but also in the space and time density of these orders. Traffic affects our fulfillment times quite a bit. Weather, of course. The shopper abilities are very different. And there's also cancellations on the day of that needs to be accounted for. And because of the variance, we need to account for it somehow, and we need to define some cost functions to account for the variance. Let's say we expected something and we staffed based on this expectation, but on the day of, the demand is very different. And let's say we got lower orders than what we expected, then we would have staffed higher than what's desired, and that would mean some of the shoppers would sit idle, and that presents an idleness cost, and that needs to be accounted for. On the other hand, if we do not staff enough shoppers and we get more demand than what we expected, then we will lose deliveries because we'll have to stop accepting orders. And if these are in-store shoppers, then we will lose out on efficiency because we will have to do more volume through the full service model, and that's bad for our efficiency. So these cost functions also need to be accounted for. So finally, let's put all this together. We have a system where we have a demand that's variable. We have store locations, a shopper pool with like varied abilities, the fulfillment times and the noise associated with it. And then finally, we have the cancellation probabilities. And we have several constraints and trade-offs to make. The handoff versus full service decision, the trade-off between idleness, efficiency, and utilization. Store timings. Costco has very different timings from Whole Foods, very different from Safeway. Shift length requirements. Our in-store shoppers are actually part-time employees, and there are legal requirements around how we staff them, when we staff them, that needs to be adhered in this formulation. And then we have around 150 or 60 retail partners, and they all have some rule or the other that we must honor. So finally, we have outputs that need to come out of the system, which is, of course, how many shoppers we need. And there are also some secondary outputs, like what percentage of the volume needs to be done through the handoff model. And we can also try to get a sense of what efficiency we might get if we staff the way we want. Now, this is a very complicated system. There's so much variance, so much noise. And there was a time in Instacart's history where we were doing this with Excel spreadsheets. And the way we were doing it was, and this was handled mostly by our operations team before we ramped up on data science efforts. We would start off with a seed value for the number of shoppers we need. And depending on what happened the previous week, we would sort of course correct. So if we had 10 shoppers and only 50% of them were utilized, we would staff only 5 for the next week. And let's say if we had 10 shoppers and we had 5% lost deliveries or 10% lost deliveries, we would bump this up to like 11 or 12 shoppers for the next week. So it was just a course correction, and it has the tendency to settle in a local optimum. And it's also not looking into all these trade-offs and the handoff versus full service decision and all these things. So we needed something that's better, and we needed something that is not based on single point estimates. So we decided to go with simulation, especially because there's so much variance. We decided to go with Monte Carlo simulations and try to optimize using the data from all the simulations. And that's what we did. What we created was an ideal universe. So we would sample from the demand distribution. We would sample from the shopper ability distribution. We would sample from the fulfillment times distribution and create this universe where there are some orders, some shoppers, some store locations, and we need to fulfill them. And how do we do this? We have a fulfillment algorithm that runs every minute in real time. We take the orders that we get and we try to create routes and deliver them to the customer. So we apply the same algorithm in this simulated universe. And the reason we do this is because one of our objectives is also to increase our efficiency as much as possible. So it's kind of cheating our way through this by actually using our fulfillment algorithm and figuring out, okay, if we want to maximize efficiency, how do we build the trips and routes? And let's work backwards from there. So if we have these trips, then because every order has a due window, there is like a start time and end, there's like 8 to 9 p.m. or 7 to 8 a.m. that for every order. So we can work backwards from there and figure out, okay, for this trip to be fulfilled on time, we need shoppers during this time of the day. And if you do this across all the trips and you aggregate the results, then you can get some sense of how many shoppers you need per hour. So that's what we did. And if you take the results from one such universe, and this is like in one store, you might get a curve like this that represents on the y-axis the number of shoppers you need, and on the x-axis the hour of the day. Then this is just from one universe. But if you do this over and over again from hundreds of universes by repetitive sampling, then you get like this huge spread of the number of shoppers we need at every given hour. Now, but we finally need one set of parameters. We need one set of staffing levels that represent all these different universes. So we need something like this. But how do we get there? Let's say the gray line is the staffing requirements from one such simulated universe. And the red line is what we want to get. Let's say all those variables, x8, x9, x10, are variables that determine how many shoppers we need in that hour. And these set of variables are fixed across all the universes. And there are two regions there. The regions marked by 1 are places where we would have staffed more shoppers than what's required in that universe if we go by the red line. That means we would have an idleness cost. In regions marked by 2, we do not have enough shoppers and that would mean we either lose out on efficiency or we will lose on deliveries. And all these universes have losses like this, and we have to minimize all these losses across all the different universes. So you can create an integer programming formulation where your variables are these x, 8, x9, so on, and you have objectives, which are basically the cost functions, and you minimize the objectives across all the universes and try to figure out what the variables should be. I'm not presenting any of the formulation details here, but you can imagine that it works, and it finally produces something like this, where for each store and for the full service shoppers, we can figure out, we finally get an output of how many shoppers we need. And that's it. Questions? Yeah, sure. So we sampled from the previous orders to create the demand distribution. So we have a forecast that comes every day. Okay, this is the forecast for Monday in San Francisco, whatever that number might be. And then we looked at the forecast error over the last few days, and we sort of built a distribution for the forecast. And we would say, okay, it may not be just whatever that forecast number is. It might be anywhere from this to this. So we created, we sampled those many number of deliveries for each data point on this distribution. And similarly for the fulfillment times, we know that we predict some time that it would take to deliver an order. But in reality, it might not be that time. So it might be a few minutes off from what we predicted. So that's another distribution. Now we take all these distributions and just sample from these to create these universes. So they're all independent universes, but we sample from the same distribution for each. Yeah. What? Sorry. Okay. Well, we have the demand, the speeds of shoppers, the fulfillment times, and those are the main things. And we apply the cancellation probability towards the very end. We would say, okay, this is the number of shoppers we need, but probably these many guys are going to cancel. So think of it like the airline overbooking. I don't want to use that example, especially with United and all that. But it's sort of the same way, but the inverse of it. But you had a second question too. No, it's very basic. We just sample from whatever these distributions are, and we sort of put all these parameters together, and we create a demand, we create a set of shoppers, we create, and we add some noise on the fulfillment times.
You mentioned about the efficiency. You have to hire the employees of the stores also as part of employees?
Yeah, it was not a conscious effort. It just turned out to be convenient that way.
I was thinking, wouldn't it, I know you guys just not about part of this, but would it have been more efficient to have the partners, the retailers themselves, take the risk of bagging it to you and then share the profits?
Yeah, in some cases, the retailers want to do the picking themselves, and they're very strict about it. So we have some partnerships which are like that, but majority of our partnerships are this way, like we hire the shoppers. Retailers might have several reasons why they want or do not want to do this. Oh, we have an algorithm that we use to actually fulfill our orders in real time. It uses a mixture of integer programming and some heuristics to figure out all the trips that needs to be created, given a set of orders and set of shoppers. It's sort of like this assignment problem.
How happy are you with the results of this?
Actually pretty happy because it's a step increase from what we were doing in the past with the course correction model. And more than the results, because we are trying to account for every single thing, we have a very good holistic understanding of what's going on. on a given day, if something is wrong or if something doesn't make sense, we know exactly why that happened. And it's also helping our operations teams try to correct these. Let's say we expect some shopper speed, but on the day of we do not see that, then probably something happened on the operations side. And this is able to highlight all these nuances that we weren't capturing with like a very basic approach that we were doing in the past. You mean the site traffic or the actual street traffic? Yeah, so we have features in our predictive models. We have predictive models to figure out how much time it takes to deliver an order or drive to the store. And there are features to account for traffic, bad weather, special events, all these different kind of things. And these models are actually better than Google's because they also have to capture for the parking time. And when Google gives you a prediction, it just gets your prediction from point A to point B. Whereas a lot of times, especially in dense neighborhoods, our shoppers spend some time figuring out where to park. Yes, it does. Probably not that important, but there might be some correlation, especially the demand might get affected by, the density of the demand might get affected by what we did on that day. If there was some issue or outage or anything like that, it might skew things, but we are still consuming that noise. Right? Thank you all. Thanks, Jagannath.
All right. How's the volume? Good? Up a little bit in the back, I hear. Is that better? Okay, awesome. So, great talk, Jagannath. One of the things I love about working at Instacart is that you can talk about space-time, density, and not do it in kind of a facetious way. Like it's a real thing that we actually care about, and we're not doing astrophysics. I'm going to talk about deep learning at Instacart. My name is Jeremy Stanley. I am the VP of Data Science here at Instacart. I spend most of my time focused on machine learning. And I'm really going to cover three things. The first one is related to a blog post, the deep learning with emojis, not math. A number of you said that you'd read this post. I want to talk to you before the talk. If so, I'm going to mostly say the same things. I'll give you a little more context as I go along, but it's essentially the same content. And then I want to talk about the future of deep learning at Instacart, which may or may not involve flying carrots. I'll let you be the judge of how likely that is to be. And then at the end, I want to talk about ice cream, because everybody loves ice cream, right? So why not talk about ice cream? All right, so let's talk about deep learning with emojis and not math. So Instacart, our value proposition, you may understand this already. It was probably pretty clear from Jagannath's talk. But what we do is pretty straightforward. We deliver groceries from stores you already know and love to your doorstep in as little as an hour. That's it. Pretty simple, right? Behind the scenes, there's actually an awful lot of complexity. We have the consumer-facing applications, our search and discovery infrastructure, but we also have the logistics infrastructure that Jagannath just talked about, and we have the applications that our shoppers use in the stores. So if you are thinking about picking groceries, maybe you've got an Instacart order and you've got all of these different items that you need to find. The first thing that happens is those items are rendered in our shopper application and sorted in a list. Ideally in a list that's going to be efficient for the shopper to find them in the specific store location that they're shopping in. And then the shopper is going to go through that list and pick individual items literally off the shelves of the store. They're then going to scan the barcode of that item to verify that they have the exact right flavor and fat content of Greek yogurt that the customer wanted. And if they don't find that exact product, we'll make a replacement suggestion. They'll triage that with the customer in real time. So lots of interesting problems across this whole spectrum. What we're really going to focus on here is how do you sort that list? So what's the right way to take the 50 items that the customer has ordered and sort them in that list for efficiency? So this is pretty difficult. Jagannath talked some about the scale that we have. You know, we're shopping out of hundreds of retailers. We've got 160 different partners now. They all have very different inventory, different store layout, different amount of information they know about what products are on the shelves and where those products are on the shelves. We shop out of thousands of individual store locations with tens of thousands of shoppers and literally millions of products in the catalog that could be found. And so doing this is, you know, not a trivial thing. It's not the kind of thing that you can just throw human labor at and solve. And so you might be thinking, well, wait a second, why are we doing deep learning? Aren't there easier ways to solve this problem? Can't you just build warehouses? Well, the answer is no, we can't build warehouses. Why? We offer Instacart across the nation. We're gonna cover 80% of the markets in the US by the end of next year. We would have to build an awful lot of warehouses to do that. You know, the beauty is that the warehouses are already there. They're just called grocery stores, and we're gonna pick out of those warehouses. So we can't build warehouses, it's not our model. Can we get the store data? Well, sometimes. You know, some of our stores really operate like warehouses themselves. They know, you know, with pretty high precision, exactly what product ought to be on this segment of that shelf at this height. And they know roughly how many they have in the store. Most of them, though, even the ones that are really good, they don't actually know how many are out on the floor of the store versus in the back, right? Waiting to be placed out front. And other of our stores are more like haunted houses than warehouses, right? There's a person sitting in the back and they know a truck showed up this morning with a bunch of watermelons and it's somewhere over there. And that's kind of the level of inventory accuracy that they might have. So we can't always get store data. Can we just map everything manually? Can't we send people into the stores to look for every single item and draw it out on a map and then use that? Well, yes, we can, and we do. We do that for testing, but you can't do it at tens of thousands of store locations. It doesn't scale. And then finally, can't you just map it all with tech? Can't you just use robots? Can't you do more kind of, you know, technology-driven things? And the answer is yes, but, you know, not quite yet. Maybe we'll get there soon. So whenever the answer to a hard problem is, you know, no or not yet, what you do is you just take it and you spread deep learning on it. So, you know, that's the kind of overarching message of this talk. And so that's what we did. So fortunately, we actually got more than just a case study of trying deep learning. We actually got some good results. And so I'll talk you through that. So the way that we think about this is you can plot on the x-axis the size of the batch. This is how many items the shopper is picking when they're picking an order. And then on the y-axis is the shopper speed. How many items per minute are they picking? And so higher is better. And so we started out with a control sorting variant, a pretty naive algorithm of, you know, basically pick produce first and frozen last and randomly sort things in the middle, just hope for the best, right? And what you find is that as the batch size increases, the shopper speed increases, which actually makes sense. Why? You have more item density in the store. And so the shoppers are going to be walking shorter distances. They'll be less likely to have to go search for something because they'll just happen to encounter it as they go. We then tested a human-based strategy of let's go into the stores, let's try to identify the clusters of products in the stores, and let's try to come up with an intuition for how you might move through those products. What might be the most, you know, likely way you would do it if you had an order. And we can just then take that overall kind of sorting within each of these stores and render that sorting for any individual set of products. So still fairly naive. It beats the control by a healthy margin. We then tried something else, which was just a traveling salesman solution, sitting on top of the inter-item picking times. And we did some simple things to try to denoise those inter-item picking times. But probably not as sophisticated as we could be. And so this is actually an area that we're investing in now to try to make it significantly better and see whether or not it can be competitive with the approach I'll talk about today. But in the end, in the A/B test that we ran, that TSP solution was as good as the human solution. And then we deployed the deep learning approach, which is actually modeling the sequence that the shoppers take and then showing that sequence back to them for the fastest shoppers. And that beat all of the others. And in fact, if you look at kind of the margin of difference over the human, it's about a 50% improvement, especially at the larger batch sizes over human as compared to the control. So why does this matter? If you think about Instacart, we're looking at, say, 125 million households in the United States. And if we can get to 5% market share and get the one trip per week, which is about typical for somebody that's an Instacart Express member, if we saved just 1 minute on each of those trips, it would be 618 years of shopping saved every year. And it's the particularly painful kind of shopping where you know you need something and you don't know where it is, right? You've lost something and it's out of order, right? So it's a pretty big impact. So to help frame the problem, we really like to use emojis at Instacart because there are so many of them in the kind of food palette. It's just a lot of fun. And so if you think about an order that started with corn and it ended with coffee, well, we can observe the sequence that a specific shopper picked all of these items in, right? We see them scanning the UPC codes on the products. We see them weighing the products if they're a loose weight item. And so the question is, can we learn those sequences? And if we can learn the sequences, we can then predict them for arbitrary shoppers and use those predictions to sort the list in the app. And so we can reframe this. Let's suppose we're halfway through and the shopper has picked the bread. The question is, which product is going to be next? Of the cookie, chocolate, pizza, chicken, and coffee, which of those products is going to be chosen next by the shopper? In this case, it was actually the cookie. Well, we can reframe this in emoji math as what's the probability that the next item is cookie, given the last item is bread, and you have a set of candidates, right? That's crucial. You can't just look at the probability of a cookie following bread. Why can't you do that? Why do you have to consider those candidates? Well, it's because some of these products are far more common than others, right? If you think about, maybe the chocolate bar is a rare kind of chocolate bar, right? It's not something purchased very often. The probability that it's going to follow bread in just random pairs of picks is very, very low because it's very rare. And so, but yet the probability just naively that it would follow bread in this order, might be 1 out of 5 because there's only 5 candidates. And so considering the candidates is a crucial part of this problem and a crucial part of the solution. So let's build up an initial naive architecture, right? The kind of thing that you start with and then figure out how to refine. We need to take the bread on one side, and we need to ultimately get to the probability that we're going to pick a cookie next. Along the way, we ought to consider that we've only got these 5 candidates. And so let's build up that architecture. Well, so the first thing we can do is we can take our million different products and we can embed them into, say, a 10-dimensional space using an embedding layer, right? And so now we are going to learn vector representation of all of these different products that tells us something about those products, their similarities, where they might be located in the store, and how shoppers might pick them. We can also embed the store itself. There's 1,000 different stores, so we're going to spend 10,000 parameters embedding the store into a 10-dimensional space. And then we can also embed the shoppers themselves. 10,000 different shoppers, that's going to spend about 100,000 parameters embedding in a 10-dimensional space. You then concatenate all of those embeddings together. You get a length 30 tensor if you're using TensorFlow. And that length 30 tensor can feed into a sequence of hidden layers. Maybe you spend around 700,000 parameters in that sequence of hidden layers and ultimately produce on the right-hand side a final vector of length 10. Then we need to think about these candidates. And so we need to take that vector of 10, which is a kind of compressed representation of what product's likely to come next. Given you don't yet know anything about which ones are candidates. It's just kind of generally where might you go after bread. We need to fan back out to the space of 1 million potential products, right? And so this is kind of almost a reverse embedding to go back to the million space of potential products. And then we can mask just the candidates that we care about. And so only allow for an activation there if it's in the candidate set. And you end up with a probability distribution over these 5 candidates. And that will give you a predicted chance that the next one is cookie. In this case, maybe the chance that it's cookie is 32%. You can then feed that into the cross entropy loss function, along with the fact that yes, cookie was in fact the product chosen next. And that gives you, this kind of score that you're going to back propagate through all of the weights on the left-hand side to ultimately try to get this probability as high as you possibly can for this specific case. But then you want to do it over, right, many different millions of picks. So that's the initial naive architecture. Let me pause here real quick. Questions about this initial architecture before I go on? Yeah.
What's the objective of the whole process? You're trying to save time, trying to make a better process?
Yeah, so the objective was kind of the A/B test that we talked about earlier. We want to sort the list such that the shoppers can move through that list as fast as possible. And so we want them to be able to pick faster. And if we can ultimately show them the list and not have to have them scroll back and forth, or maybe go out of the logical order in the store because the list is long and it's presented in the wrong way, that saves a lot of time.
A naive question, but there is a concept called variance statement operation research.
Yes. So that was one of the things that we tested on just the picking times themselves. You can't do a TSP on the location of the items because A, the location of the items isn't known. B, you'd also have to know all of the things that are interrupting your travel through the store. C, shoppers want to pick the produce first and the frozen last. They want to pick the rare items first in case they're out of stock so they can communicate with the customer. So the TSP formulation isn't obvious that it would work even if you had perfect data. So other questions about the initial architecture? Yeah, in the back. Yeah. So you take a 26-sided die and you roll it, and you see what it comes up with, and you try that. Honestly, there's many different hyperparameters in any deep learning model, right? The size of your embeddings, how many hidden layers you use, how many units are in each of those hidden layers, what the learning rate is, how much patience you're going to have. And you can ultimately do hyperparameter optimization over all of them. I would say that more often than not, for me, that hyperparameter optimization happens fairly late in the game. And early on, you're trying lots of different architectures and experimenting. You're maybe only working with a subset of the data. And so it's a bit of an art to try to navigate through what's the right architecture and hyperparameters before you get to a point where you might do a full-scale optimization. Yeah. Yeah. So we're actually modeling everybody. We, in the end, just predict for the fastest shoppers, but we're modeling everyone so we don't throw out data.
So is training data, are you looking at how many times cookie was picked, or how many times cookie was the optimal?
Yeah, so we're actually looking at how many times it was picked. We don't know what optimal is. We're just trying to model the behavior of our shoppers. If we can learn their behavior, maybe we can take the best of them and help the others mimic their behavior. That's the essence of this. So let me hold more questions because I'm going to get through the second half of this and we can take more questions on this and a couple of other things. Okay, so first, you can do this in 51 lines of Keras. And those 51 lines are in the blog post. If you don't believe me, if you think I'm just making this up, I drew little lines showing you, like literally all of the different pieces of the architecture mapped to very specific, simple Keras calls. So there are, though, some interesting things that we can learn just from this simple model. Let's take the embedding of the products themselves. And we can take that embedding and project it from 10 dimensions down into 2 using T-state, right? So we're going to preserve kind of the orientation of all of the data and its relationship spatially, but compress it down into 2 dimensions. And the first thing that you see is that there's actually a lot of structure in those 2 dimensions. Like clearly, some of these products are closely related to each other. And that's useful information to the model. It's learned those relationships. What's funny is this wasn't trained using anything about the aisle or the department that the products were in. And so if you just overlay that as a color, it's learned the aisle and department structure. It's kind of learned, if you will, a 10-dimensional representation of the prototypical store that can then be used with any individual store to kind of distort it into what that store's structure should look like. And what's kind of cool is this is the meat and seafood department. So all of these blue dots are meat and seafood, but there's a bunch of like green dots in here and orange dots. And there are things that are stored by the meat and seafood counter, but they're not meat and seafood. They might be tools or spice rubs, or maybe they've got lemons there sometimes, right? And sometimes it makes sense to pick those lemons there. And so it will learn that sometimes these products don't actually organize in a way that the structured metadata might suggest. So there are 3 big problems with this architecture. The first one is these 2 are kind of redundant. right? I talked about an embedding that takes the products into 10 dimensions, and then later I've got another 10 million parameters, the same number of parameters here, that's gonna fan back out to 1 million dimensions. And so those things are doing kind of similar things, and I'm wasting a whole bunch of parameters. So I'd like not to do that. I could reduce the variance without sacrificing any bias if I can get rid of that duplication of parameters. The second one is, in my naive implementation, these million length vectors are kind of dense and represented in a dense way in memory, and that just slows everything down. Most of them are masked out, but you still have to reserve all of that memory and update the masks, and it's not a very efficient way to do it in the back end. The final thing, and this is kind of subtle, is there's no way to inject additional data about these candidate products. So if I wanted to use the aisle and the metadata that I have, the aisle or the department, or I wanted to use the product names or the product images, I could feed them all over on the left-hand side, put them into LSTMs or convolutional neural networks or do other embeddings and pass them in on the left-hand side, but they would all relate to the bread. How would I take an image of the chocolate and have that affect this? I can't. It's not possible. So because I've kind of projected back out, there's no way to feed additional information in. And so I'm kind of limited with how much additional data I can use to understand the candidates that are being considered. So we're gonna fix those problems. Let's get rid of all of this stuff on the right-hand side and just focus on the left-hand side. Let's take the chocolate and move it over to the left-hand side. This is kind of the key idea. You know, take your candidates and consider them also on the left-hand side. Well, what I can do is I can share an embedding here. Use the same 10 million parameters, the same representation into 10 dimensions, and I can feed the chocolate through that shared embedding and the bread through that shared embedding. And now instead of just 30, I get a vector of length 40. That can all go through the hidden layers. And on the right-hand side, I can produce a score. It doesn't really matter what that score is right now. It's just think about it as it's roughly something that's going to be proportional to how likely the chocolate would be chosen next, given you just had bread. But for now, it's just giving me a score, and it's giving me a score of 0.7. So now I've got this scoring kind of sub-architecture. Let's take all of that and kind of just encapsulate it. Let's call it a score generator. We'll put it up in the right-hand side. Remember that it's doing all of the stuff that I just described. But that score generator has in total 10.81 million parameters. And really what it's doing is it's taking the chocolate in and it's producing a score. And not to lie, it's also taking in the fact that we had bread last and that we're at a specific store, that we've got a specific shopper. So all of those things are happening and we're spending 10.81 million parameters. Now I can distribute that score generator over all of the candidates. In Keras, it's something called the time distributed layer. And I can reuse it. I can take the chicken and I can feed it in instead of the chocolate. And maybe the chicken comes out with a score of minus 0.2, meaning it's somewhat less likely to be chosen. It's not a very good candidate after the bread. And so on, right? We can do it for all of the 5 candidates. And maybe the coffee is actually the least likely to be chosen next. Cookie is pretty good, right? It's a baked item. There's a good chance cookies are going to be near the bread. And there's a decent chance that it would be near the bread as well. So I get scores coming out of the score generator that's shared for all of the different candidates. All of those scores can be fed into a softmax, right? You exponentiate them, you normalize them, they become a probability distribution over just my 5 candidates. And I get a prediction. In this case, maybe the cookie's 36% chance likely to be chosen next. That goes into cross entropy, along with the fact that cookie was chosen next, and voila, we have an architecture that's much, much more concise and elegant. And now we can feed in things like the text description of the products, the images of the products, the aisle and metadata, and they can all be shared in this score generator, processing both the candidate and the prior item at the same time. It also trains a lot faster. So we got about 10x faster training time. Ultimately, the models that we're training in production take something like 6 or 7 hours. So they go from 60 to 70 hours to 6 or 7 hours is a pretty big gain. We got about 10% improvement in accuracy. So to give you a sense, we're accurate about 60% of the time. So we're never going to perfectly guess what the shopper is going to pick next because shoppers do random things all the time, right? It's going to be impossible to get it exactly right. But going from 50% to 60%, that's a pretty huge gain in accuracy. The predictions were slower. This takes about 2 times longer to score in production. And in part, that's because we're doing this in multiple passes through the network, right? It's not happening in a single pass. And so it's a little bit more computationally expensive at runtime, but in the end, we're talking about 100 milliseconds versus 50 milliseconds. That's not a big concern for us. We've got time. This isn't like something we have to do instantaneously. We can queue them up if need be. So for production, that slowdown in scoring speeds didn't really matter. So let me pause here. Questions about this as an alternative architecture? Yeah.
Say anything about the chauffeur or the family. Because that's how it happens, right?
Oh, for sure. So there's a whole nother angle to this of like, what does the consumer buy? How do we present things to the consumer? That's independent. This is kind of, at this point, they've expressed their desire in the basket, and we're just trying to pick it as efficiently as possible. So I'll talk more about some of the problems that relate to the customer after this. Yes? So the accuracy in this case, the say 60% accuracy is, what's the chance that we're right, at any given point in the pick? That given, in this case, these 5 things, that we choose the one that the shopper did in fact go and pick in the past. Yeah, remember the buyer is, the consumer is just setting the stage. They're just saying, these are the 50 things I want you to go find. We're trying to predict, given those 50 things, what's the sequence? There in the back. So to add the metadata, we definitely need more parameters. This 10.81 million is going to go up. But it doesn't change the fundamental notion of this architecture, that if we've got a convolutional, a set of, like you use ImageNet and pre-trained ImageNet to take the images of the products, and you get out a vector on the right-hand side. You can use the same ImageNet coefficients on both, and if you do something to then maybe modify that with a simple linear transformation at the end, those coefficients can be the exact same. So anything can be shared in this architecture, and you kind of get it for free both on the prior and the candidate. Yeah, in front of that gentleman, yes. Yeah. Yeah, so that's a great question. So the stores, it wasn't super obvious. It clearly learns the warehouse. The fact that like warehouse in our vernacular is that Whole Foods is different from Target. But I think you'd really have to go into the stores and understand that, well, this is a Whole Foods in Columbus Circle. It's actually 3 levels, and it's very different from a Whole Foods in Potrero Hill, which is one giant open space, as an example. So it's going to be learning the idiosyncrasies of the layouts of the stores. For the shoppers, I think it's a little bit more interesting. It learns the shoppers' preference to go clockwise versus counterclockwise in a store. It learns their preference to always pick produce first or frozen last. And then it ultimately learns, how well does the shopper know the store? As Jagannath mentioned, some of the shoppers are dedicated to the store. They know the store really, really well. Others are just walking in like you or I might. They don't know the store very well at all, and they may take more of a random walk. Okay, so let me move on. We can take more questions at the end. This is the team behind this work. Francisco is the designer. Montana is the machine learning engineer, and Nima is the product manager. And to give you a sense of how we work, this is a laptop with a Jupyter notebook running in it with an early version of this scoring algorithm. And it's inside of a Whole Foods. So Montana and myself are walking through Whole Foods, laptop in a grocery shopping cart for hours, going, well, no, it had us go get the frozen yogurt. That doesn't make any sense. And asking the person, who's actually stocking the store, where exactly is this item? We didn't buy anything, and nobody seemed to care. This is just the valley for you, right? It's only in San Francisco. Okay. So let's talk about the future. So there's a bunch of different problems we can apply deep learning to. We're in various stages of development and testing on several of these. One of them is searching. So if you're a consumer and you come to the Instacart site, you're going to enter in a query. And maybe that query is pickled carrot organic baby. What does that mean? It could very well be that you want organic baby carrots, and for some reason you type pickle. You know, I don't know. Some people do this. It could be that you wanted baby food that was organic and was carrots, right? Could be equally a good fit for this query. Or maybe you wanted organic baby pickles, and you know, maybe you were hoping those organic baby pickles would actually be pickled carrots, not pickled cucumber. That might actually exist. I think you can get those someplace. And the question is, what's the ranking, right? How do we sort these for the user? And it's going to be a function of the query itself. So you can imagine this going into, you know, LSTM. It's going to be a function of all the product data. We've got the images, we've got the price, we've got the product name and the description. It's going to be a function of the specific user. If this is me, I've bought these baby carrots before. And so we ought to raise its rank for me because I've already bought that in the past. There's a good chance I'll buy it again. It's also going to be a function of the community. People really like these carrots, and so it's more likely I might buy them because the community likes them. All of these are signals that can be woven together to optimally rank search results. Another really interesting application is product replacements. So we get to the store, and it turns out you want a ghee, and it's not there, right? What do we give you instead? How many of you, raise your hand if you know what ghee is? So maybe a third of folks. So ghee it's clarified butter, and it's used in Indian cooking. And you take the ghee in its clarified form, and you use it like you would any other oil, only it tastes really, really good. And so we replace it with, algorithms in the past replace it with butter. And if you know how to make ghee, you can do it from butter. But it's like a 2-hour ordeal, right? You've got to cook at a very low temperature. You've got to skim all of the whey off. So this is basically us telling the customer, like, stop being so lazy. Just make the ghee yourself. Take this butter. Everything's going to be fine. Our customers hate that replacement. Another really bad replacement is when the customer orders cooked eggs, and we just give them regular eggs. It's like, come on, dude, just cook the eggs yourself. How hard is it? Another really bad one is when they order rice cauliflower, and we give them white rice. This has happened to me. Like, just because they have rice in the name and they're both frozen and they look the same. Cauliflower and actual rice, very, very different things. You would never want to substitute one for the other in a recipe. Or my final favorite one is the customer orders the field roast, which is a vegan brand of sausages. And we say, okay, well, we'll just give you regular sausage, right? It's just both sausage. So you can imagine this is a pretty important problem where customers really care about these replacements. And it's very nuanced, right? It's a function of the type of product, the circumstance. You want to use the image, but you're going to want to use the text, the nutritional data, many different components. Another really interesting one is I talked about how our stores don't know where things are. Well, we've got tens of thousands of shoppers moving through those stores all of the time. They can easily capture video or photography of the shelves. If we can identify the million products, on the shelves, we'll know exactly where those products are and how many of them there might be, and we'll be able to manage the not founds and replacements because we have better inventory information. So that's a really interesting problem. A final one is, what if we could help our shoppers find better parking places? We see where they park at different store locations. We see where they park at different delivery locations. It's very noisy data, but we could take the Google Maps images themselves and help identify potential parking spaces along with the real-time signals that we get from our shoppers and actually speed up the delivery times by helping them find better parking spots. So those are some of the ways we could use deep learning. Last but not least, I'm almost done. My voice is going to go, so I've got to finish quickly, is ice cream, right? Got to talk about ice cream. So why ice cream? Well, Instacart released an open data set today. How many of you saw the blog post? Nobody. Well, I'm really glad. Well, maybe 2 people. I'm really glad I'm talking about it. So we released 3 million Instacart orders. And we wrote a blog post. You can find it on tech.instacart.com. And we just put it out there. We'll launch a machine learning competition around this data, but you'll feel free to download it and analyze it and work with it in advance. So what's in it? So it really starts with 3.4 million orders from about 206,000 users. And we've got the order ID, the sequence of orders, the day of week, the hour of day, how many days it's been since that user placed an order before that order. We also have the product data, which is relatively simple. It's just the product, its name, the full text description of the product, the aisle and department of the product. And then we have a table that links these two together, about 30 million rows, showing for every one of these 3 million plus orders, exactly which of these products were purchased in what sequence. And so what does it really look like in practice? Well, this is the first user. They bought soda, almond milk, beef jerky, popcorn, and then paper towels. And then they came back and they bought soda, pistachios, beef jerky, bananas, popcorn, and Cinnamon Toast Crunch. So you can already see some interesting things, right? 3 of the items they repurchased, and then they started to buy some other things as well. So you can use this, we use data like this to sort the buy it again aisle on the Instacart interface. So you've purchased maybe hundreds or thousands of products over many orders. How do we help you navigate that? Well, we can predict which ones are going to buy next and just present them to you. You can shop in a minute instead of 10 minutes. That's what I do. Literally, I can shop on Instacart in less than a minute. Another interesting application is to recommend items. You just bought avocados. What are the other items, given your background and your purchase history, that you'd be most likely to buy next? So why ice cream? Because we looked at what people eat and how they consume these foods over the course of the day when they're ordering. And specifically, we took some of the most common products and we asked the question, what are the most common products are purchased earliest in the morning? And what are the most common products are purchased latest in the day? And what we found is if you look at the products that were purchased early in the morning, these green 25 curves, it's things like Cheez-It crackers, snacks, 0-calorie soda, right? Dry roasted almonds and apples and trail mix, like healthy things, right? Aspirational foods. What do you think people buy at night? So these are the 25 foods that people buy at night. The first 24 are all ice cream. The 25th one is frozen pizza. Yeah, at least there's a little bit of protein in that frozen pizza or something, I don't know. And so if you dig into this, the second most commonly or latest purchased product is the Tonight Dough, right? Which is appropriate. You should buy that at night because you're gonna watch the Tonight Show and it's all branded around that. And the first one is Half-Baked. And I'm gonna let you make your own judgment about why people are buying that late at night. I don't do that stuff. So we thought it'd be fun. We actually got some ice cream from Instacart. We have it here if you want to have it after the talk's done. I think we tried to get these flavors. I think we bought all of them. Oh, no, I see thumbs up. We actually got them. Sweet, they actually had it. Yeah. So that's it. I'm Jeremy Stanley. You can find me on Twitter at JeremyStan, or that's my email address, jeremy.stanley@Instacart. I'll post these slides and put them on the Meetup group so you can find the slides. We're hiring. Just go to careers.instacart.com, or you can talk to Nicole or to Shadi. They work with me on recruiting if you're interested in opportunities here. Thanks so much for coming. And I want to do one more round of applause for Jagannath. Really appreciated his talk as well. So I'm sensitive to time. It's about 8:13. Maybe if you want 1 or 2 more questions, and then we'll break. Yes. So question, and because you're asking the last question, you get a book. Yeah, you're welcome. I hope it's a good question. If it's a bad question, I'll take the book back.
Yeah.
Yeah, so the question is, the optimization problem could be a candidate for reinforcement learning. And I think you may be right. You can't, it's akin to Go. You can't brute force solve it. It's just computationally impossible. And if you think about how they solved the Go problem, it was a combination of predicting out into the future, using that to do tree-based search more efficiently, ultimately evaluating the candidacy of the solutions. I think there are similar frameworks to that we can use. I'm not sure if reinforcement learning can be used, but I'd be interested to talk about it more. Cool. Other questions? So you've asked if you back in the back. So how are the data science teams structured? So the machine learning folks, about 15 or 16 folks that do machine learning, they're directly integrated into product teams. And so these are kind of mission-driven teams. There's a team that controls the shopper app. And if you're doing machine learning, you report into the technical lead for that team. In some cases, the technical leads are themselves people with a machine learning or data science background. And the whole team, engineers, machine learning people, product designers, mobile engineers, they're all working on the same problem, same mission. And the machine learning is a kind of key component. It's a tool. Everybody wants it to succeed. So that's really the organizational model. And my job is to kind of link all of those people across all of the teams together. So I want to stop with the public questions so folks can get ice cream. I'll be up here. Jagannath can come back up to the front if you want to ask more questions as well. Thanks so much. Yeah, so okay, come get your book.